As a pot of tea cools, the temperature of the tea is modeled by a differentiable function h for 0 is less than or equal to t is less than or equal to 10, where time t is measured in minutes and temperature h of t is measured in degrees Celsius. Values of h of t at selected values of time t are shown in the table above. So that's right over there. Use the data in the table to approximate the rate at which the temperature of the tea is changing at time t equals 3.5. Show the computations that lead to your answer. So they give us a bunch of points. So let's just graph this just so we can visualize what this data is telling us a little bit. And I suspect that this might be useful. So this right over here is our temperature axis. This is our temperature at any moment in degrees Celsius, and then this is our time axis, and they gave us the time at 0, 2, 5, 9, and 10. But they give us the temperature at those times. So this is 0, 2, 5 is a little bit further, 5, 9, and then 10. And at time 0, the temperature is 66 degrees Celsius. 66, so it's right over there. At time 2, it is 60 degrees Celsius. At time 2, it is 60 degrees Celsius. At time 5, it is 52 degrees Celsius. So time 5, maybe it's right over here. This is 52 degrees Celsius. At time 9, or after 9 minutes, I should say, it's at 44 degrees Celsius. So this is 44 degrees Celsius. And after 10 minutes, it's at 43 degrees Celsius. So this is really just a graph showing how it cools off over those 10 minutes. Over those 10 minutes. That's what the data is telling us. It's kind of a curve like this, and we've sampled it at these points. So going back to part A, use the data in the table to approximate the rate at which the temperature of the tea is changing at time t equals 3.5. So the rate of change is really just the slope of this curve at time t is equal to 3.5. So really, we just want to find the slope at that point right over there. We want to find the slope. And we don't know the actual function, so the best way to approximate the slope at that point is really just find the slope between minute 5 and minute 2. So the rate of change, so we could say that the rate is going to be approximately our change in temperature over those 3 minutes. So h of 5 minus h of 2, and this is obviously going to be in degrees Celsius, over the number of minutes that changed. So we end at 5 minutes and we started at 2 minutes. And so the rate is going to be approximately, at 5 minutes our temperature is 52 degrees. At 2 minutes our temperature is 60 degrees. And then this is over a change in 3 minutes. 5 minus 2 is 3. So this gets us, we scroll to the right a little bit, this gives us negative 8 degrees Celsius over 3 minutes. Or the rate at 3.5 minutes is going to be approximately negative 8/3 degrees Celsius per minute. So that is part A. And then part B. Using correct units, explain the meaning of 1 over 10 times the definite integral from 0 to 10 of h of t dt in the context of this problem. Use a trapezoidal sum with the 4 subintervals indicated by the table to estimate this thing. So the integral from 0 to 10 of h of t is really the area of this entire, under this curve right over here. That's the integral, that's this part right over here. And then we're going to divide that by 10. So what this is really giving us, this expression right over here is the average, temperature. This is the average temperature over that time period. The integral of the temperature function divided by the total amount of time that has elapsed. And then using correct units, well, it's the average temperature. The average temperature is once again going to be in degrees Celsius. And it makes sense because this right over here is in degrees Celsius. You're multiplying it by time right over here. But then you could divide by, you're dividing, I'm assuming, by time right over here. So this is times minutes divided by minutes. So then you just get degrees Celsius again. So this expression right over here is just the average temperature over those 10 minutes. Then they say use a trapezoidal sum with the 4 subintervals indicated by the table to estimate this. So the trapezoidal sum is, we don't know the exact function here, so we won't be able to analytically evaluate this definite integral. But what we can do is divide this area into 4 sections. They tell us to use this, 4 subintervals, and we'll essentially divide it into 4 trapezoids. So this is one trapezoid right over here. So this is one trapezoid right over there. That's my first trapezoid from 0 to 2 on the base, and you see on the left end of that trapezoid its height is 66, the right end is 60, and then the next trapezoid will go from 2 to 5. Let me do that in a color that contrasts a little bit better. The next trapezoid will go from 2 to 5. Next trapezoid goes from 2 to 5, and then the third trapezoid goes from 5 to 9. The third trapezoid goes from 5 to 9. And then the fourth trapezoid goes from 9 to 10. Goes from 9 to 10. And so if I want to approximate the definite integral part right here, before we divide by 10, I just need to find the area of these 4 trapezoids. So let's do that. The area of this first trapezoid is going to be the base, which is 2, times the average height. The height on the left side of this trapezoid is 66. The height on the right side of this trapezoid is 60. The average height right over here is going to be 63, just the average of 60 and 66. So this area right over here is 126. That's the area of the green part right over there. By the same logic, the area of this orange part, I want to do that in the orange color. The area of this orange part, the base right over here is 3. Base is 3. And then the average height, the height over here is 60. The height over here is 52. They're 8 apart, so the average is going to be 4 away from each of them. It's going to be 56. So the area here is going to be 3 times 56, which is 150 plus 18. 150 plus 18 is 168. That's the area of this orange trapezoid. And then the area of this blue trapezoid, the base right over here is 4. And then the average height, the height here is 52, the height here is 44. The average of 52 and 44, let's see, they are 8 apart. 8 apart, so then it's just going to be 4 from each of these, so it's 48. So the average height here is 48. And so 4 times 48 is 160 plus 32, so it's 192. And then finally, this last trapezoid, its base is only 1. Its base right over here is only 1. And then its height is 43 at the left side, 43 at the right side. So its average height is 43.5. 43.5. So it's 43.5 times 1. So that's just going to be 43.5. And so if we add up the areas the areas of all these trapezoids, we have a pretty good approximation for the definite integral. I'll just use the calculator for this part right over here. So we have 126 plus 168 plus 192 plus 43.5 gives us 529.5. So this is equal to 529.5. And so that's our approximation for the definite integral part, but then we also have to divide it by 10, or we have to multiply it times 1/10. So we've evaluated, so this part right over here, we got 529.5 as our approximation. It's not going to be exact, but using the trapezoidal sum, the sum of the areas of these trapezoids. And now we have to multiply it by 1/10. So let's do that. So, or we can just divide by 10, which actually we don't need a calculator for that. 52.95. So this whole thing evaluates to 52.95. And I'll do the next 2 parts in the next video.